Everybody, welcome to the afternoon session for HATRA, and we're going to have a talk and then a discussion session. And so the talk is going to be on information control made simple, which is something I would dearly love. And it's by Henant Gooney and Jonathan Aldrich, and Henant is going to present the talk.
Great, thanks for the introduction. Just flip on my shirt. Okay, cool. Yeah, so for the past several months, I've been working on making information flow control simple, or at the very least, and maybe more modestly, simpler. But first, before we get into any of that, it's worth asking, why bother with information flow, right? So the thing I've been doing is sort of looking at the existing, great work on information flow control, the fundamental theory, and going, okay, this is really good. How do we slice this up in a different way and put a nicer user interface on it to make it more presentable and easier to use? So, but why is it worth doing any of that? Why bother with any of this? And to try and explore this question, it's worth looking at something like SEO4, which is this formally verified microkernel. And the actual kernel itself is only about 10,000 lines of code. Clearly, they didn't spend 2 decades writing 10,000 lines of code. The proofs or the specifications about the kernel are more than 1 million lines of code. So clearly, this is where the cool, important stuff is happening. And what the proofs actually prove are these two properties. The first of them being confidentiality, which is essentially the property that, in the abstract, that secret information doesn't leak out of the kernel. And the second one being integrity, which is the dual property that untrusted or unsecured information can't compromise the kernel. So these are the two fundamental information flow properties. And at the end of the day, these two properties that SEO4 can guarantee that it has are why we care about SEO4, right? It's why SEO4 is such an impressive achievement. If SEO4 didn't guarantee confidentiality and integrity, there really wouldn't be much else to it, right? These two properties are what we care about, and really, once it boils down to it, the reason information flow control is cool, at least to me, is that it lets you sort of reason very directly about these properties, about confidentiality and integrity, without having to sort of resort to a heavyweight theorem prover like SEO4 has had to do with Isabelle/Hall, where they spent tens of developer hours per line of code, of kernel code. That's not tenable, right? There are lots of programs out there that you might want to guarantee these properties for, and information flow control is one way of potentially doing that in a maybe more straightforward way. And okay, so if information flow control is so cool, why doesn't everybody use it, right? It's not a new idea. I can come up with it, obviously. It's been around for decades. Why isn't it in wider use than it is currently? And to try and begin to explore this, it's worth looking at this flow diagram of a simple web application, right? So if you give me the benefit of the doubt with this diagram, there are thousands, if not hundreds of thousands of programs out there that look like this, and thousands more are being created constantly, right, every day. So there's some module in the program that communicates with the network. There's some module in the program that communicates with some database, and there's some interesting application logic between those two modules. In this case, some input validation and some password checking that does something useful, hopefully, right? And in this diagram, these green arrows denote the flows that the application needs in order to function, right? They're essential to the application's sort of core functionality. And dually, or conversely, these red arrows, these red dotted arrows, are the flows that the application needs to prevent in order to prevent its own compromise, right? So you see here that the red arrow skipping from network I/O to password check directly without going through the input validation module. That's a bad flow because the password checking module maybe has some interface that says, okay, basically as a precondition, my input has to be input validated. I assume that this is the case, and if you're not doing that, then it potentially compromises the password checking module, and that's not good, right? And to try and begin to think about how you'd specify this in a classical IFC system, so one of the first thing that the system is going to give you is this lattice for confidentiality. So it's going to give you this lattice, and it's going to say, okay, the bottom of this lattice is low confidentiality, and the top of this lattice is high confidentiality. And essentially, flows up the lattice are going to be fine, but flows down the lattice are not going to be fine, right? We have to prevent flows from places that have highly secured information to places that are not secured, right? Because that represents a potential compromise of information flow of secrets. And dually, if you want to verify integrity, the system is going to do something very similar. It's going to give you another lattice, and it's going to say, okay, the bottom of this lattice is low integrity, the top of this lattice is high integrity, and essentially flows down the lattice are fine, but flows up the lattice are going to be prevented, which is the opposite of how it is in the confidentiality lattice. And right off the bat, even with this like brutally simplified flow architecture, you see that there's this like very not simple inversion of reasoning that you need to go through like mentally in order to process what's really happening here. Like this doesn't really map very nicely to the diagram up there, right? So for example, if in this very simple example, data from the network I/O module combines with data from the database module, right? You're going to need to compute a least upper bound in the confidentiality lattice to figure out that okay, if those two pieces of data combine, confidentiality-wise, the output data is going to have a label of DB handle. And but for integrity, if the same thing happens, you're going to need to compute a greatest lower bound within the context of the lattice again to figure out that okay, the output data is going to have this network I/O label, right? And what you run into, even if for the simplified scenario, this is easy for you, like it probably is for everyone. What you run into is if you complexify this even a little bit more, it gets prohibitively complicated to sort of do these lattice operations in your head. Like really fundamentally, what you care about is specifying those flows in the diagram. You shouldn't have to be thinking about lattices at all, right? The lattices are just a kind of an abstraction that we've come up with, a natural abstraction, but nonetheless a maybe unnecessary abstraction for talking about the fundamental properties. And really, this is what we're seeking to address. So this is the core of our system. So essentially what we're trying to do is we're trying to take the stuff in the diagram and just put it into textual format, right? So this first rule here is corresponds to the red arrow between the network I/O module and the password checking module. And it says, okay, flows from the network I/O module to the password checking module are going to be banned, right? They're going to be prohibited. And similarly, these next two rules just codify the bidirectional red arrow between network I/O and database handle, right? They say, okay, those two rules basically say, okay, those two modules can't directly communicate. And there's something I sort of haven't addressed here, which is that, or I guess I sort of talked about it, but in this diagram, transitive flows are allowed, but direct flows are not in certain cases, right? So between network I/O and password checking, between those two modules. The way information flow systems classically deal with this is through these like two operations, declassify and endorse. The first of these corresponds to confidentiality, and the second of these corresponds to integrity. For that, we also have a unified treatment, which we just call allow. Basically, the whole idea of our system is looking at the interface presented by IOC systems while preserving the theory and saying, okay, how do we present a unified treatment of all these really fundamentally interesting concepts in a way that doesn't introduce the complications of previous systems. And right off the bat, once you look at these rules, something you might think is, okay, that's cool and all, like for your really simplified flow diagram that like works really well, I guess. But like, isn't a problem going to be that like, okay, will you not need like way too many rules? Like, aren't you going to get like an n times n like combinatorial explosion of rules that you need to specify? And we thought this too. So we looked at a couple like real applications in Rust. So the first of these is Rocket, which is a super popular like HTTP framework, and Rust is the most popular one actually. And it turns out that if you want to do information flow control on this like part of Rocket that manages like the bytes, the raw bytes of a TLS key that you've given it, in order so it can establish SSL connections. The part of it that deals with that is really quite self-contained. Like Rocket does all this like very, very complicated stuff like database connection pooling, like thread management, like HTTP connection pooling, all that stuff. But the part of it that deals with TLS connections is really quite self-contained and quite simple, right? So you don't need to like concern yourself with all the nasty parts of the application that do all this complicated stuff. You just get to reason about that. And for the other application we looked at, which was Conduit, which is this like chat server written in Rust for the Matrix protocol. It's this federated chat server that works kind of like email. For the keys Conduit manages within the context of the Matrix protocol, you run into a similar thing where, okay, it does all this like ridiculously complicated stuff that like modern chat services have to do, but at the end of the day, the part that you actually want to do IFC reasoning about is like really, really like it's you really don't have to interact with much else of the application beyond like the modules of the application that correspond directly to key management. So hopefully that sort of quells your fears for now, but we'll look at the stuff, the work we did in Rocket in just a bit. for now, we're going to go through this kind of simple and kind of silly example that sort of walks you through the basic elements of our IFC system. This is written in like pseudo Rust. It doesn't actually correspond to Rust semantics. So don't read too closely into it. Really just pay attention to the constructs, to the IFC constructs that are being used in here. So first off, we declare a flow rule. We say that the sec variable can't flow into the network socket that we have as a local variable here. So sec contains a password and an IP address, and the socket is a network socket. We're saying that the password data, the secure data, can't flow into the network socket. And almost immediately, we have an opening curly brace, and we override this flow rule, right? And okay, what does overriding mean? So it's actually a concept unique to our system. When any arbitrary flow happens in our IFC system, the way it decides whether that flow will be allowed or denied is by looking for the most specific rule that applies to that current to that particular flow, or the most, or rather the most specific set of rules, right? So here, because sec.second is flowing to sock, right? It's going to look at the rules in the current context, which is this one and this one, and it's going to realize, okay, this is the most specific rule that applies to it, and that's an allow rule, so the flow will be allowed. It's going to be permitted, and then there's no error there. And so there's a few interesting things happening here, or really, this is really why overriding is so cool, is because we just get to reuse the existing lexical scoping mechanisms of the language in order to sort of do potentially dangerous operations, and then after we've done the dangerous operations, just end the lexical scope and go on to do like safe operations that are verified to be safe by the IFC system. So here, when we try to do effectively the same flow as we did up here, we're going to get an error from the IFC system because this rule has actually gone out of scope at the closing curly brace. And if you've written some Rust, you know that this is actually kind of an idiomatic Rust pattern. Like people do this a lot to when they're using unsafe, for example, to restrict like pointer provenances and stuff. Oh, whoops. Okay, so we're going to move on to the case study. So I talked about this very briefly, but okay. So really, what we're going to be mostly concerned with is this part of Rocket, which I've kind of tried to simplify and ellipsize. If you look at the part of the Rocket code base that actually does this, it's not going to look exactly like this. I've actually kind of modified it for presentation purposes. Like it doesn't use an either type up there. I've modified it so it's easier to do IFC reasoning on. So just keep that in mind. Essentially, we're concerned with this because this is where Rocket like sets up TLS, right? This is the most information flow control sensitive part of Rocket, like anywhere on Rocket, if what you're concerned with is managing TLS keys. And specifically, we're going to care about this self.config.tls.key thing, which contains the raw bytes of some TLS key that you've given it. Okay, so just stepping through the functionality of the code here before we get into any interesting IFC reasoning stuff. So the red there is where Rocket sets up like the default TCP socket that it's going to use to accept connections in the absence of a valid TLS configuration. The orange there checks that the application actually has a valid TLS configuration. Basically, it checks that you've enabled it and that you have a valid config. The green there marshals Rocket's TLS configurations structures into Rust TLS native configuration structures. The details aren't important. Basically, it's marshaling structures from one place to another in order to work with the Rust TLS cryptography primitive library. And then finally here, it's going to, if all of that succeeds, it's going to create the TLS socket and set it as the default socket to use. And the TLS socket is going to be able to decrypt and encrypt packets. And importantly, something that's notable about this is once you've gotten to this point, it's not actually possible to access the raw key data anymore, and Rocket doesn't actually need the raw key data anymore, right? The key is going to be encapsulated inside this TLS listener : bind abstraction, or the TLS listener abstraction really, and you're not going to get like you're not going to be able to access the key anymore once you've created that socket out of it. All you're going to be able to do with the keys is decrypt and encrypt packets, just the operations that you need to do in order to manage TLS connections. So stepping into the interesting part of this, so the red here, so the red and orange like flow declarations up there are something that you're going to see a lot with our system. essentially what the red one does is it prevents the thing that we care about that we care about information flow wise from flowing to like side effecting functions like transitively. And the orange thing there is going to prevent the key from flowing to any like local variables. And just a small aside about the orange rule, we got a reviewer comment asking, okay, like why do you guys actually care about like flows to local variables, right? Like at the end of the day, like what you care about is that like sensitive data doesn't leak to. Oh, you're using a telescope. Do I need to? Should I zoom it in? Okay. Right. Where was I? Right. So at the end of the day, what you actually care about is that like the thing that you want to do information flow control on, like doesn't leak to the outside world, right? Like what you care about is that it doesn't leak to the network, that it doesn't leak to standard I/O, that it doesn't leak to some other place outside of your program that might do malicious things with it, right? So why do you care at all about flows to local variables? And the reason is abstraction, right? So it's not obvious immediately, and it's actually a very good question. The reason is abstraction, because if you want to have these like module level flow guarantees that I showed you at the beginning of the presentation, you need to be able to enforce like locally within your own program that modules communicate in a certain way, right? And in order to do that soundly, you need to be able to enforce within those modules that functions and variables and all these other things communicate in ways that are safe, right? You can't just immediately state the interesting properties of like, okay, my thing doesn't interact with side effecting functions in these bad ways. Something that you have to do for abstraction purposes is do IFC on local variables. And then the green here, so these are overrides. So essentially, what's happening here is that so we're declaring this variable, and the orange rule the rule highlighted in orange prevents the key data from flowing to any local variables, right? So you get this problem here where, since it's prevented from flowing to local variables, if you bind a local variable and then initialize it to something that contains key data, then the IFC system is going to raise a red flag and say, okay, that flow is banned. Like you're not allowed to do that. And we use overrides to deal with this, except it's a special kind of override. It's not really special, but it's like syntactic sugar that for dealing with like the case of binding and initializing something at the same time. And this actually deserves some more explanation. So what this actually desugars to directly is, so if you have this kind of thing, where you have a binding and then you want to declare a flow rule on it, like in the same breath that you're binding it, what actually happens is that uses this Rust feature where it lets you like separately bind and initialize something. So it actually desugars to like, okay, I declare the variable and then I declare the flow rule, the overriding flow rule importantly, so I don't get an error from the IC system. Then after I do that, I'm going to reassign the variable, or I'm going to initialize the variable to the data that I was originally going to use it with. So it's a way to bind and initialize and declare a flow rule on a variable at the same time without having to step through the kind of ugly separate syntax there. It's really just trivial syntactic sugar. Right. So these are all overrides, like I mentioned, and then because all of these are overrides, this call right here is permitted specifically because of this. So this allows the key data to flow to the listener local variable, and this function doesn't use any side effecting things. We know that from our analysis. We know transitively doesn't use any side effecting, like it doesn't have any side effecting functionality inside of it. And then finally, I mentioned the last time I sort of looked at this call that, okay, once you call a TLS listener : bind, the sort of normal abstraction mechanisms of the language have taken over. And at that point, you don't really need the IFC system anymore because you can't actually use this thing to get at the key. So it's so here in the green, we do this. We use the allow construct that I talked about before. And what allow does is it takes an expression and it evaluates the expression and it returns the value, but without any of the dependencies that the IFC system is tracking on that value. So essentially, allow is a way to coerce the IFC system into saying like, okay, like you know what you're doing. I'm hands off here. Like there's some architectural thing going on here that I can't reason about. Like go ahead, do what you want. And that sounds really bad. And it's kind of a problem endemic to IFC. But I'll try and argue later on that it's not actually like that big of a problem. So weaknesses. Actually, I guess I'll talk about it here. So you saw at the end of the last slide that we used that scary allow construct. It's so I called it a coercion, and it's kind of reasonable to think of it that way, but really, if you're thinking about the human aspects of using that kind of thing, it's very easy to audit like uses of allow, right? Like if you think about it, right, allow is just this like textual is just this like textual thing you put in your program that tells the IFC system to disengage. It would be very easy to put put in your CI that okay, if I get a pull request or if I get a merge request that uses an allow in a place where it's not on the whitelist, right? Then just fail, right? Like give me an error from the CI. Don't merge this. Like raise red flag. Really, what allow is it's a way to specify the architecture of your software. I think, or at least I think that's a more productive way to think about it, because I think whenever you use an allow, it really indicates something fundamental about like, okay, like data flows. I've specified that data is supposed to flow through my program in these particular ways. If I use an allow, it means that I'm independently validating that whatever I'm doing is safe, and that architecturally something is going on that makes sense according to like what I actually need to happen information flow wise. So really, it's an additional way to specify like flow architecture if you want to think about it that way. But I do agree that it is a problem that you could address with more stack analysis, and there is work on that called robust classification, which we haven't addressed. And okay, so no user studies. So this is the big one. I'm at HATRA, and I'm claiming that the system I've designed is so much simpler and it's so much cooler. But I don't have any user studies to validate it. That's true. That just is a weakness. I'm not going to excuse myself from that one. I would like to have user studies soon in order to sort of validate some of the things I'm saying here. But at the end of the day, without that, I can't really claim that my system is actually simpler or actually presents a better interface than prior work without validating it against users. And finally, I think I haven't talked about this very much, but I think lattices might still be neat as a way of. I have this idea that lattices, I think, are still more powerful than what I presented here. And I think that the strength of our system is that it's actually not very powerful. And I think at the end of the day, you really don't have to throw out very much of the existing work on information flow control in order to use our system. I think it would not be very difficult to sort of macro express the system within like Java information flow control or like FlowCamel or one of the existing like popular systems. I think really something that makes our system possible to adopt is that it's actually completely compatible with the existing lattice-based theories. You would just need some sort of like trivial translation from our system to lattice-based systems, which I think is just kind of worth pointing out at the very least. And okay, so I don't have user studies, but I do have this. There are these 14 things called Green's cognitive dimensions of notations, which are like userless ways to evaluate if you like given a specification system, like how easy it is to use. And I'll try to argue using this, at least that our system is pretty usable. So progressive evaluation essentially says like how easy is it to obtain feedback on partial solutions. So I think our system fares pretty well on this, just because it's like I mentioned, right? It reuses the existing lexical scoping mechanisms of the language. So if you only want to do some interesting information flow control thing locally, all you have to do is start doing IFC in some lexical scope, and then once that lexical scope ends, like the system is totally disengaged. There's not necessarily a soundness problem. It's just that you're only talking about IFC within that lexical scope. Okay, consistency. After part of the notation has been learned, how much can be guessed? So I didn't actually talk about how we handle functions, but it's really elegant. Just for time's sake, I did talk about it. So a lot of IFC systems have to, in order to be fully general, they have to add like special kinds to the type system in order to deal with like label polymorphism and all that kind of stuff. We don't have to do that. We don't actually extend the type system at all, except for like tracking dependencies really, and like declaring rules, I guess. So I think really a core strength of our system is that once you know the very the very basic rules that I've listed here, like that's really all you need to know to use our system, right? And I was actually giving a different presentation on this a couple months ago after I sort of drafted this. I was talking to someone whose research interests are usable security, and she was saying, oh, like once you have your tool, like this might be a really great way to teach like information flow control to like undergraduate students, right, in one of her classes, because this really follows intuitively from how you think diagrammatically about information flow control, I think. And it really doesn't add anything to the language that isn't explicitly about information flow control. Okay, so closeness and mapping. I think on this axis we're pretty strong as well. So I agree that in the abstract, it might be more natural to think about the problem of information flow control in terms of a lattice, right? Okay, like in the abstract, I'm thinking about it and I'm like, okay, in my program, I'm going to have these security labels like A, B, C, and D. I'm going to define a partial order over them, and boom, that's a lattice. But I think I've given at least some evidence here that the abstractions you end up with, i.e., a lattice at the user interface level at least, are not ideal for actually like scaling and doing information flow control in like very, very large programs. I think it quickly becomes untenable, like given the mental overhead that you have to go through with that sort of thing. That like a more declarative approach, like our rules here, is perhaps preferable. And I sort of alluded to this just now, but like in one sentence, like our system doesn't require you to like compute like least upper bounds and greatest lower bounds and work with new kinds in the type system and learn new kinds of polymorphism and all these other things, right? We really just reuse everything in the language to the greatest extent possible, and we never require you to reason about lattices in your head because that's like hard. Like you don't want to do that if you don't have to. Okay, so what's next? So soundness. So a proof is currently in progress. So we have a full formal system formalized as an extension to the ROS type system. We've got a version of progress and preservation adapted to the setting of IFC. So I guess the proof is literally in progress. It's in the progress portion of the progress and preservation. I think I know how to do preservation as well. It's just a matter of sitting down and doing it. User studies. I mentioned this. I would love to have those. And implementation, finally. So the whole point of this is to like make an actual tool that people can use on real programs, hopefully, and like get it into people's hands and and into the real world, and then see how it fares, and iterate on the things I've said here using the feedback from that. Oh, there's supposed to be a final slide. Oh well. Yeah. So thank you. I think to conclude, I think actually support the thing I said at the beginning of this presentation, which is that like I've genuinely made information flow control simpler. I think at the very least, what you should take away from this presentation, if anything, is that lattices are maybe not a good user interface decision, even if they work out mathematically really well. And secondly, like information flow control is like really cool, and it's a really great way to address a lot of the security properties that you want to address in real world programs. And it's worth exploring ways to make it more reusable, even if that doesn't end up being the system I presented here. Great, that's it.
Thank you. All right, so we've got time for some quick questions. So, Jonathan, you said you'd like to see if there's any questions in the audience.
You can speak into the microphone so that those online can hear you.
Yeah.
Awesome.
Great.
Marco? Yes. So I just got a top class paper on a very similar topic.
Oh.
And one of the things that we sort of consider is indeed how appropriate it is to use a lattice. In the sense that if you relax the lattice, in particular you relax that you need a single unique upper bound given any two term, you can actually get, for example, both confidentiality and integrity to be represented with the same like set of labels that at that point just have a simple sort of typing, during the sense without the requirement of a lattice.
Sure.
No, I just think it's a nice coincidence in the sense that two works basically at the same time are discussing if lattices are opportune for this kind of approach.
Yeah, I think it's a natural thing to think about, really, because I think the past 20 years of work have really been on like okay, like just like doing program analysis and information flow control is really hard. Like, and lattices make that, like, make the formalization and implementation of it, much easier, I think.
At least upper bound, you should not even be here.
Exactly. It's very easy to just derive a lattice from the fundamental problem of information flow control and ascribe mathematical meaning to it that way. But I think we're getting to the point where the theories have progressed far enough, and real world use hasn't progressed far enough that maybe it's time to start considering, like, okay, like how's the interface of this going to work, and I think that's very interesting.
Cool. So actually, I had a question as well, which is that, so all of the examples that you had were the modifications to the information flow policy were in the same function body as the modules that the flow was going to. So I was wondering what would happen if I split one of those across function boundaries. So can functions declare preconditions about the information flow for their parameters?
Yes. They absolutely can, and that's actually how our version of function calls work. That's how we get polymorphism naturally. We actually the way function calls work, which I didn't show off because of time constraints, is basically that the called function declares a bunch of information flow rules on its parameters, and then we do a compatibility check between the caller and the callee context, like symbolically, to figure out, like, okay, can you actually call this function? And it turns out that if you do this compatibility check the correct way, then you don't actually need a separate version of polymorphism in your system. You basically get to reuse the language's existing polymorphism mechanisms very naturally. So the answer is yes, you can do that, and that is how it works.
Cool. Yeah. All right. I think we should thank the speaker.